A structure we see quite often in electronics is a junction. They're usually pretty easy to spot, and we know the electric current into one must equal the current out. That's Kirchhoff's junction rule. You may have heard this go by a different name. Kirchhoff's first law is pretty common. Kirchhoff's current law is also a standard in many places. But I prefer the junction rule because it keeps our focus in the right place, on the structure we can actually see. So what exactly is a junction anyway? It's a single point in a circuit where at least 3 wires come together. Why do I say at least 3? Because 2 is the same as 1. The charge just flows through and that's it. 3 wires gives the current an opportunity to either split or combine. But it's not limited to 3. These are all examples of junctions. To be clear, we don't actually know the values of these electric currents up front. The whole point in the junction rule is to give us an equation to solve for them. But you don't even know how many currents you have unless you find the junctions first. This simple circuit has 2 junctions, here and here. When you're drawing electric currents, it's best to start from one junction and travel along a segment until you reach another junction. This is all the same current. A junction is the only reason it would ever change. Is that why we say we've reached a junction in our lives when we have to adapt to changes? Anyway, we can do this same process on the other segments, and now we know how many different currents we have. There are 3 in this case. The junction rule tells us how those currents split or combine. They actually split through this first junction here and then recombine at the other. Because of that, the second junction isn't actually telling us anything new. The junction rule works out the same for both. This is a pattern you'll see with more complex circuits too. No matter how many junctions there are, you'll probably only ever need about half of them. But how do we know this rule is true? How did Gustav Kirchhoff figure it out 180 years ago? He didn't just pull this out of his butt. He was a physicist, don't be ridiculous. He based this junction rule on an established law of physics, conservation of electric charge. It's the idea that charge can neither be created nor destroyed, it can only be moved around. If you have a wire junction, any charges coming in must go out. Not only that, each individual charge can only take one path in and one path out. A single charge isn't going to magically combine with another or split in half, but the overall collection can combine or split. Since each charge comes in from somewhere and goes out somewhere, the total current in must equal the total current out. Bingo bango? Not so fast. Electric charge and electric current are not the same thing. Electric charge is the stuff that's flowing. Electric current is the flow rate of that stuff. Conservation of charge alone doesn't say that anything flowing in must flow out. It only says charge can neither be created nor destroyed. As far as the conservation law is concerned, the charge could flow in and then pile up in the junction. I am not implying charge does that in a junction. It definitely does not. I'm just saying the junction rule requires a bit more thought to justify. Electric current is the flow of positive electric charge. So let's start by considering 2 positive charges. Out in the open, they'll both repel each other and fly away. But in this wire, each charge is surrounded by a bunch of other charges, keeping them from moving left or right. The wire itself also keeps each charge bounded, so they can't move up or down. They're stuck by all these interactions. If one of them gets nudged hard enough though, they'll repel the next one forward and start a domino effect. That domino effect is transmitted at nearly the speed of light through the wire, and the flow reaches equilibrium across the entire circuit almost instantly. Wire junctions are no exception. Charges don't have a chance to pile up in a junction because they're too busy repelling each other. The reality is a little more complicated than this, but it's good enough for our purposes today. Okay, now that we have all the pieces, let's derive Kirchhoff's junction rule. First, we know every electric charge that enters must leave. Second, we know those charges don't pile up in the junction, so the rate at which charges enter must equal the rate at which they leave. What's the flow rate of electric charge? That's electric current. We write this as total current in equals total current out. That's it. That's the Junction rule. Bingo bango. And until next time, remember, it's okay to be a little crazy. But I prefer the Junction rule. Do I really want to do quotes there? This is a pattern you'll see with more It's the idea that a single charge isn't going to magically combine with an, slow down.